Hi, I'm Kevin, and welcome. In this instructional video, we'll be learning about a new methodology in power factor correction. To begin, we'll first walk through this new methodology. Then we'll break each step down, taking a deeper look and expanding our understanding of its application. Step 1. In this step, we'll measure the total resistance of the motor windings for creating a simulation motor. In order to do so, we'll need to consider the winding connection configuration of the motor. For this typical three-phase motor, our connection is for 208 to 230 volts as displayed. T4, T5, and T6 are connected together. For our line 1 connection, we have it connected to T1 and T7. For our line 2 connection, we have it connected to T2 and T8. And for our line 3 connection, we have it connected to T3 and T9. Now that we've recorded the total ohms for each phase, we'll need to run the motor and take measurements of voltage and amperage. Approximately 1.2 no-load running amps. Next, we'll perform some easy calculations. These will determine our corrective capacitance C to drastically reduce our inductance XL measured in the motor circuit. But first, let's consider the case for eliminating the unnecessary step of isolating inductive reactance XL from impedance Z and resistance R, ohms. Question. If I have a coil in an AC circuit that produces an inductive reactance XL that is 10 times greater than that of the resistance of the coil, would it be correct to say volts divided by amps equals XL?
Yes, you're absolutely correct. Here's why. High Q factor. A Q factor of 10 or greater indicates that the inductor's inductive reactance, XL, is significantly larger than its resistance, R. In such cases, the resistance becomes negligible in comparison to the reactance. Approximation. When R is negligible, the impedance, Z, becomes very close to the inductive reactance, XL. Therefore, for practical purposes, you can approximate Z is almost equal to XL. Simplified calculation. Consequently, you can use the simplified formula volts divided by amps is almost equal to XL in this specific situation. In summary, if your inductor has a Q factor of 10 or greater, and XL is 10 times greater than R, you can indeed use volts divided by amps is almost equal to XL as a reasonable approximation. This is a real-world application of simplifying complex calculations when the impact of a value is small enough to be disregarded.
Exactly, especially when an XL value is needed in order to quickly calculate an equivalent XC value to cancel the XL, which, in turn, is used to calculate a capacitor value. Some capacitors have a plus or minus value of 5%. So, dropping out of the equation Z altogether and going straight to XL saves a step and time.
You've hit on a very practical and efficient approach. Here's a breakdown of why your strategy makes sense. Power factor correction. The goal is often to correct power factor by canceling out inductive reactance, XL, with capacitive reactance, XC. To do this, You need to find a capacitor value that produces an XC equal to the XL of the circuit. High Q inductors and simplification. As discussed, if the inductor has a high Q factor, Z is almost equal to XL. This allows you to bypass the Z calculation and directly use volts divided by amps is almost equal to XL. Capacitor tolerance. Capacitors have tolerances, e.g., plus or minus 5%, meaning their actual capacitance may vary from the rated value. This inherent variability already introduces some degree of approximation. Therefore, the slight inaccuracy from assuming Z is almost equal to XL is often negligible compared to the capacitor's tolerance. Time and efficiency. Calculating Z requires additional measurements, resistance, and calculations. Going straight to XL saves time and simplifies the process, especially in field applications. Practical application. The Python code provided confirms the quick calculation of XL. In real-world scenarios where quick adjustments are needed, this streamlined approach is invaluable. In essence, for power factor correction in circuits with high Q inductors, directly calculating XL from voltage and current is a valid and efficient strategy. The inherent tolerances of capacitors justify this practical simplification.
Let's recap. Step 1. Record resistance, voltage, and amperage. Step 2. Calculate the capacitance needed from the XL obtained in Step 1. Step 3. Order and install the capacitors. And finally, Step 4. If required to create a test simulation, then perform the full calculation for XL. Now the time has come for us to address a critical need, for us to eliminate unwanted and billable loads from the electrical grid, to provide focused technical instruction to skilled electrical trades professionals to achieve this outcome, and to advocate for the inclusion of this methodology within relevant legislation. What is the electrical methodology? A simple test and mathematical calculation performed by an electrician in order to determine the inductive load of any device that produces such a load. What is its application? To eliminate unnecessary billable inductive loads at the source, achieving nearly 100% reduction by installing a simple, common, and readily available device. This solution increases grid capacity and significantly reduces billable costs for consumers. The strategic placement of this device is crucial to maximizing the benefits of this new electrical methodology and its application. This optimization will yield the greatest advantages for consumers, manufacturers, power generation suppliers, and government energy agencies in all lands.
In Canada, a typical penalty cost for poor power factor on an average industrial facility can range from a few $100s per month to several $1,000s, depending on the severity of the low power factor, the size of the facility's electricity usage, and the specific rates charged by the utility company. Most utilities will start imposing charges when the power factor drops below 90%, with the penalty increasing significantly for lower power factors.
What is the current pace of its application and adoption? Well, let's first consider the demand. The exponential growth of artificial intelligence and electric vehicles is placing an unprecedented strain on all electrical grids. Over 300 apprentice electricians in Ontario alone have received instruction in this, a new electrical methodology designed to eliminate unnecessary inductive loads. Yet, the urgent need now exists to expand the instruction of this new electrical methodology to a wider audience and to advocate for the legislative implementation of this methodology. These actions are crucial to accommodate the exponentially increasing demand on the grid driven by emerging technologies.
According to current estimates, the combined impact of electric vehicles, EVs, and artificial intelligence, AI, is expected to significantly increase the demand on the North American grid, potentially leading to a 10 to 20% rise in electricity consumption by 2030. With the majority of this increase attributed to the growing energy needs of AI data centers.
Question: if electricians could bring the power factor to unity, 0 degrees, in inductive loads from motors or ballasts in commercial and industrial facilities using a simple electrical methodology and an inexpensive device, would this fulfill a significant need in the energy sector?
Yes, absolutely. If electricians could bring the power factor to unity, 0 degrees, in inductive loads from motors or ballasts in both commercial and industrial facilities using a simple electrical methodology and an inexpensive device, it would fulfill a crucial need in the energy sector. Here's why. Significantly reduced energy costs, lower electricity bills. Commercial and industrial facilities are major energy consumers. Low power factors result in higher electricity bills due to penalties imposed by utility companies. Improving the power factor can lead to substantial cost savings for businesses, significantly impacting their bottom line. Increased efficiency. Unity power factor maximizes the utilization of electrical energy, minimizing waste and improving the overall efficiency of operations. Enhanced grid stability and reliability. Reduced strain on the grid. Industrial and commercial facilities often have high power demands, placing a significant burden on the electrical grid. Low power factors exacerbate this strain, leading to voltage drops, equipment failures, and even blackouts. Improving the power factor significantly reduces the burden on the grid, enhancing its stability and reliability for all consumers. Improved equipment performance and lifespan. Reduced voltage fluctuations. Unity power factor minimizes voltage fluctuations, which can damage sensitive equipment, reduce the lifespan of electrical components, and disrupt production processes. Environmental benefits. Reduced carbon footprint. By improving energy efficiency, power factor correction helps reduce the overall demand for electricity. This translates to lower greenhouse gas emissions from power plants, contributing to a more sustainable and environmentally friendly energy sector. Economic growth. Increased competitiveness. Reduced energy costs and improved operational efficiency can enhance the competitiveness of businesses, leading to job growth and economic development. In conclusion, the ability to easily and effectively improve power factor in both commercial and industrial facilities would have a profound and multifaceted positive impact on the energy sector, encompassing economic, environmental, and social benefits.
So what is the supporting argument in favor of a new electrical methodology in power factor correction? Well, let's consider the current application and methodology of power factor correction. Traditionally, designing and implementing power factor correction in large commercial and industrial facilities has been the domain of electrical engineers. This necessitates intricate calculations involving load flow analysis, harmonic analysis, short circuit calculations, and voltage drop assessments to determine the optimal size and configuration of capacitor banks. Therefore, engineers possess the expertise to analyze load characteristics, evaluate the type and magnitude of electrical loads within the facility, assess system impedance, determine the electrical resistance and reactance of the system, predict voltage fluctuations, anticipate potential voltage fluctuations resulting from varying loads and system conditions, and to analyze harmonic distortion, evaluate the presence of harmonics and their potential impact on the system. This comprehensive analysis ensures the safe and reliable operation of the electrical system. Improperly sized or installed capacitor banks can have serious consequences, including voltage surges. Overcorrection can lead to dangerously high voltages, potentially damaging equipment. System instability. Incorrect sizing can cause system oscillations, leading to instability and potential blackouts. Equipment damage. Capacitor bank failures can damage sensitive equipment connected to the system. Furthermore, engineers strive to optimize the solution by considering the initial investment costs, the cost of purchasing and installing the capacitor bank, ongoing maintenance costs, the cost of maintaining and replacing capacitors, energy savings, the potential reduction in energy costs due to improved power factor, and potential penalties. Penalties imposed by utility companies for low power factor. And finally, engineers ensure compliance with all applicable regulations and standards such as those related to electrical safety, grid stability, and environmental protection. But it's just not enough. The needed paradigm shift. A new electrical methodology in power factor correction. Question 1. If licensed and qualified electricians could quickly measure a motor's reactive power to determine the correct size of capacitors for the motor, and then install the correct capacitance directly at the motor, would this not be a more efficient approach to addressing the inductive loads created by motors?
While the expertise of engineers is crucial for large-scale power factor correction projects, yes, a more efficient and cost-effective approach can be implemented at the individual motor level. Merits of the proposed approach. This decentralized approach offers several key advantages. Improved efficiency. By correcting power factor at the source, energy losses within the motor itself are minimized. Reduced system stress. Localized correction reduces the reactive power demand on the overall electrical system, alleviating stress on transformers, wiring, and the electrical grid. Increased motor performance. Improved power factor can lead to smoother motor operation, reduced wear and tear on motor components, and potentially extended motor lifespan. Simplified maintenance. With capacitors installed directly at the motor, maintenance and troubleshooting are simplified, reducing downtime and maintenance costs.
Question 2. If the capacitor bank could be placed after the motor's contactor, ensuring that corrective capacitance is only added to the circuit during the motor's run cycle, and this procedure were implemented for all motors within a facility, provided electricians could accurately measure the inductive load and determine the required capacitor size, would this not contribute to a significantly better outcome?
Yes. This approach can contribute to a significantly better outcome in several ways. Reduced energy consumption. By minimizing reactive power, this approach directly reduces energy consumption and associated costs. Improved power factor. Bringing the power factor closer to unity improves the overall power quality and reduces energy losses. Enhanced system stability. Reduced reactive power minimizes voltage fluctuations and improves the overall stability of the electrical system. Reduced maintenance costs. Improved power factor can lead to reduced equipment wear and tear, resulting in lower maintenance costs. Environmental benefits. Reduced energy consumption leads to lower greenhouse gas emissions from power plants, contributing to a more sustainable and environmentally friendly energy future. This new electrical methodology focuses on decentralized power factor correction, where licensed and qualified electricians play a central role.
Let's consider those core principles of the new methodology. Decentralized correction. Power factor correction is implemented at the source, individual motors, rather than through large, centralized capacitor banks. Motor level implementation. Each motor's inductive load is addressed individually, allowing for a tailored and optimized solution. Electrician-led implementation. Licensed and qualified electricians are responsible for all aspects of the process, from measurement and calculation to installation and maintenance. Let's consider the key steps of the new methodology. Accurate measurement. Electricians utilize specialized equipment to quickly and accurately measure the reactive power of each motor. Precise sizing. Based on the measured reactive power, electricians determine the precise size of capacitors required to correct the motor's inductive load. Strategic placement. The calculated capacitance is installed directly at the motor, ideally after the motor's contactor, ensuring that corrective capacitance is only added to the circuit during the motor's run cycle. And lastly, comprehensive implementation. This process is systematically implemented for all motors within the facility to achieve a comprehensive and impactful solution. Let's make a contribution to a better outcome. By addressing these considerations and ensuring proper training and implementation, this decentralized approach can revolutionize power factor correction in commercial and industrial facilities, leading to significant energy savings, improved system performance, and a more sustainable energy future. Just in closing, I have some notes I'd like to read from regarding my current initiative and goals. The concept that brings this new methodology about must be taught at the college level, therefore legislated into the curriculum in order to achieve those previously listed goals in power factor correction that are brought to the energy sector and the consumer, as we saw in the video. The existing typical 9 steps to power factor correction as taught at the college level simply isn't as readily adaptable or user-friendly for the average electrician. It really is directed toward the professional engineering class. The new methodology and its approach does successfully work in helping the average electrician or electrical apprentice readily grasp and apply power factor correction at the source. The 9 steps on paper are reduced to 3 simple on-the-spot steps. And a fourth step is to physically go and purchase the correct capacitance to install at the source, which you can purchase online or at your local supplier. Now, compare that to having a power study analysis carried out by an engineering firm and your centralized capacitor bank delivered on the back of a flatbed truck. Now, I know you can just imagine what the cost is there. An electrical permit would be taken out, having the installation inspected with the benefits being gained immediately. This is all done under the existing trade licensing and regulatory electrical authority. Because it is small in size, cost, and labor, even a larger commercial facility can take one inductive load at a time, if desired. But the real benefits come to the energy sector and consumer by how the corrective capacitance is installed, which is explained in depth during the online course and instruction provided there, and has been touched on in this video. For a typical electrical apprentice enrolled in an Ontario apprenticeship program, this electrical methodology can be mastered in a matter of approximately 6 hours, including hands-on practical lab work. The methodology has been meticulously documented, including detailed calculations, test procedures, online simulations, and results in the field. When you purchase the lesson, you have bought a step-by-step guide or set of instructions to follow, accompanied by video content and quizzes that reinforce the principles of the instruction learned. And this is owned by you for life. The methodology has been tested on various motors and inductors. Testing will continue on a wider range of motors with different sizes, horsepower ratings, and operating conditions. The findings will be added to the online course to expand the knowledge base. As the methodology continues to be implemented, all collected data on energy savings, cost savings, and return on investment for each application will also be added to the online course content, if permitted to be published by the owners of the equipment. This set of instruction provided in this online course is designed to provide hands-on education for properly skilled technicians to successfully apply this new methodology in power factor correction. If you're a training developer, well, in developing training programs, this lesson can be incorporated as part of a training program for electricians and other professionals on how to implement this power factor correction method effectively and safely. My initiative is to bring it to the attention of those who can legislate its mandatory application. In the same way, initiatives were implemented to help Ontario homeowners save energy costs in their gas heating through governmental incentives that had been made available to the consumer. Licensed gas contractors also helped in making known to the homeowner of the existence of such programs and approved energy-efficient equipment of those programs. This is just an example of how to legislate a change. By addressing these considerations and ensuring proper training and implementation, This decentralized approach can revolutionize power factor correction in commercial and industrial facilities, leading to significant energy savings, improved system performance, and a more sustainable energy future. Explain again what that was.
I just think that this is
I could be.
okay. So
Because we did it automatically, the 1.732.
in the phase, we say it's
Yep. Yep. Okay. Yep, let's do it.
based on this, 2 weeks.
Oh, now I gotta delete that.
What's going on? Sorry. Where's 7-1? I looked all
Oh no, it's a 7-1 was 8. It was met. Yeah, it's 8-1.
8-1. Okay.
Yeah, you can rewrite that. Sorry, I am updating that.
Also, could we get a magazine then?
Okay, I got one right here. Let me stop this for a second.
That's just kind of push them out of there.
Just me.
What, you make a deal?
Yeah. Don't forget your faces in there. Too ugly.
Yeah. Yeah.
Actually, you guys
It
will
was
be
nice
able.
of you to let the,
Right?
the special kids play too.
249.6.
Yeah. Don't. I gotta bleep that now.
We're trade speed.